Hi guys again. This video is a continuation of the previous one. In case you don't know what the series is about, I'm solving a bunch of official exams for the capacitor chapters. I'm starting with 12 LS now, and later on I will do the series for the same chapter for the GS, and I will continue to do so for the other chapters too. In case you need help in chapter before another, you can comment below and you can let me know so I can help you as much as I can. In case you don't know, I'm starting this series from the easiest problems in the official exams to the hardest problems. Okay, so you can find the ones that fit your level and start from there. Okay, now here I will be solving the first session for 12 LS 2023. Okay, in this problem we have obviously, as always, a battery that is charging the capacitor, okay, and we have the component D, which is the resistor, okay, and we have the positive direction of the current that is flowing from right to left, anti-clockwise, okay, counterclockwise. Now here we have an ideal battery. I'm taking what I have in the given. An ideal battery G of electromotive force E. As I said before, EB equals E minus RI. And since we don't have internal resistance and the battery is ideal, we simply can say just equals to E. A resistor D of resistance R. Okay, a capacitor initially uncharged, which means that at the beginning, at T0 equals 0, the voltage of the capacitor was 0, of capacitance C, and the switch K. Now, part 1 is a theoretical study, as I expected. We have to redraw the circuit of document 4 showing on the direction of the current. That is really easy. We all know that the current is flowing from the positive pole. This is the conventional direction that we chose, from the positive pole all the way back to the negative pole. Okay, so this is the conventional direction. You redraw the figure and you just show the direction of the current. Now in 1.2, as I said before, you can decompose your problems into few steps. It will feel a lot easier. Okay. Now here they want the differential equation for UC, and I solved this plenty of time. I solved it last time. Okay, now here we have the first step. This is 1.2. The first step is we have to start with the law of addition of voltages, or as it is known, Kirchhoff's law for some of the students. Law of addition of voltages. The voltage of the battery is giving the capacitor plus the resistor. Okay, this is the first step. The second step, we have to replace them by their formulas, which is E equals to UC. We need UC, so we keep it. Plus UR, which is the resistor, so we replace it by Ohm's law. And as I said before, we can only have UC or I or Q. Since we want UC here, I will replace I by C duc over dt, and it's also explained in the previous video. Okay, so E equals UC plus R, and I will replace I here by its formula, which is C duc over dt. Sometimes they ask for one more step, and which is we divide the whole thing by RC, so we can get to the last version of the differential equation. Since they don't want that now, I got to the formula, I simply stop. Now, the solution in 1.3, the solution of the obtained differential equation has the form A plus B, E minus T over tau, where A, B, and tau are constants. Every time they ask you about the constants or tau, or all of them together in the same questions, I also decompose them into 5 steps, which are, first, you have to rewrite the solution in front of you, which is UC equals A plus B E minus T over tau. In the last video, I said you have to expand if you have a parenthesis so you can make it easier. Since they already did that for us, we don't need the first step now, okay? So we simply jump to the second, which is we find the derivative. The derivative of a constant, which is A, is 0, obviously, plus B. B is also a constant, but since this constant is multiplied by a variable, which is the exponential of the time, so we have to simply keep it, and we keep the exponential, and we simply put a parenthesis in the middle. In the parentheses, there should be all of the constants next to the time t, which is the minus and tau. So we put the minus and the tau. And of course, we put 1 because we cannot leave the numerator empty. So what is duc over dt? It's equal to minus b over tau e minus t over tau. So this is the second step. We find duc over dt. And we expand duc, they already did that for us. Okay, and now the third step is we have to replace them in the differential equation, which is the one that we got in the previous question, which is E equals UC plus RC duc over dt. Now we replace everything concerning UC by their solutions. This is the most important part. Some people confuse it. Okay, so E, it's E, simply we keep it. UC, it's A plus B, E minus T over tau. Plus RC, we keep it, they are constants. Times the derivative is minus B over tau, E minus T over tau. And as I always say, when you have to replace some variable by its expression, preferably put it between parentheses so you don't confuse uh, your multiplications with the additions in case you're struggling with math. Okay, now I have to remove the parentheses, obviously, so I don't. If you can do them, you do it directly after the third step. If you cannot, replace UC and DUC over DT by their expressions and put it in parentheses, then continue your calculation as I'm doing right here. Okay, so since we have A plus B E minus T over tau, it is not multiplied by anything. We simply can remove the parentheses. And here we have RC multiplied by this factor. So I will keep the minus in front of all of them and I will rewrite everything because they are multiplied. Okay, now the fourth step, we have to take the exponential as a common factor always. The terms that have exponential are this one and this one. So we rewrite what's next to the exponential, which is b minus rc, b over tau. And the only thing that doesn't have an exponential is kept outside by itself, which is a. I'm sorry. And a should be e at the end. Okay, now, and the last step I have to say that e is different than 0 always. So its factor should be equal to 0. Now, the factor of e is b minus rc, b over tau. And we resolve by putting each factor on each side. Then we remove b and b. We get 1 equals rc over tau, which is tau equals rc. I'm sorry for the noise in the back. Now, this is the last step I did in the previous problem, because the only unknown I had was tau. Now I have another unknown, which is a. And since A is kept alone and E is also kept alone on the other side of the equality, I can simply say that A is equal to E. And that I got my second unknown. Okay, now the third unknown, which is B, I still don't know it and it's really important. And some people, they think they can just write B is equal to E and simply move on with it. This is incorrect. You have to solve one thing on the side for B by itself. How do we do that? We rewrite the solution. Okay, but now we rewrite it by replacing the constants that we know with their actual value, which is UC equals E. Now I know that A is E plus B E minus T over RC. Okay, and every time in physics we want to find a constant like this, we use the boundary conditions or the initial conditions. What do I mean by that? Go back to when the time was 0. What did we know at this point, at this specific time? We know that UC at this time, at T0 equals 0, was 0 volts. I can benefit from that. Why do I know it? I can use it. So let's say at T0 equals 0, UC at T0 equals 0 is equal to E plus BE minus T, which is 0. We just said that we want to use the beginning of the experiment. Okay, Now, simply, you see at the beginning was 0, so I replace it by 0, equals to e plus b. E to the power 0 is simply replaced by 1. The whole thing, e to the power 0 is 1. So times 1, I can simply just not write 1. Okay? Now what do we get? 0 equals e plus b, and we take b to the other side or e to the other side. We get that b is equal to minus e, and I got my last variable. I didn't talk about that in my last video. This is really important. It has its own solution. You cannot not write this answer because you will lose some marks, okay? Now at the end, we rewrite the solution complete. E minus e minus t over tau, which is RC, and we can take e as a common factor, which is an expression that we know, so we know that we are correct and we solve everything correctly. Okay, this is 1.3. Now, 1.4, calculate the ratio UC over E at t equals tau. At t equals tau. I know that at this time is very specific and special. Why? Because I know at this time UC doesn't have any value. It has 63% of the maximum value, which is, I know it is E. Okay, even though I don't know the value of E in the given, they didn't tell us it's 9 volts or 10 volts or whatever. Okay, but I know that the 63% is very important. So I write the ratio they're talking about, and I simply replace UC with the value that I know it should be, which is 63% or 0.63 E over E, which is a specific value that cannot be changed. It's a constant. It's not changing. Now, since we have E over E, we can simply remove them. What do we get? We get that the ratio UC over E at this specific time is 0.63, and it should be really easy. Because what is the difference? If you compare two things with each other, you have to find their ratio. So you can find the difference between. So you can find what one of them is equivalent to the other. Okay, now this is 1.4. Let me start with the second part. Measurement of the mass of an object. Now, the first thing that I can see is the graph. Once you see two graphs like this for a capacitor, you have to compare them. Like, why we have two? Why do we have two graphs, okay? The main thing they ask about here when they represent two graphs is tau. Which tau is bigger? Which time is bigger? If you want to know that, you can see which one reaches the permanent phase last. I can see that the first graph, it's very curvilinear, and it achieves the maximum value here, almost. However, the second graph, it gets to the end of the graph, at the end of the grid, and still it's not 100% reaching the maximum. So I know that the second capacitor, the second graph, it's taking a lot of time to reach the permanent phase. So the second graph is actually, or it's actually the graph that has the higher tau, the higher time. It takes a lot of time to be completely charged. Okay, now this is the first thing you have to think about when you see two graphs. Okay, then we read the questions together. Document 4 is a simplified circuit used in a digital balance where the capacitance C varies with the mass of the object placed on the balance. Two objects of respective masses M1 and M2 are placed successively on this digital balance. So we have two masses. For each object, the capacitor in the balance has a different value of capacitance. Each object has a different C. Shown in document 5, which is the graph. Represent the voltage you see as functions of time, corresponding to each of the masses M1 and M2 respectively. Given R, now we have the resistance. Great. So now we have one of the unknowns in the previous part. Using curve 1 of document 5. Okay, curve 1, this one. Indicate the value of E. We all know by now that the value of E is the maximum value on the curve, or it's the phase, or it's the value where the curve reaches its permanent phase. And clearly I can see that the permanent phase is here. It cannot get any bigger than that. It's constant. It's going through a horizontal asymptote, which is at the value of 5. So E is simply 5. If they ask you to justify, the justification would be the curve reaches its permanent phase when the voltage was 5. Okay. What I mean by permanent phase, it's when the curve appears to be horizontal on the graph. Okay. Now, 2.1.2. Determine the capacitance C1 corresponding to the object of mass M1. How can I calculate C? Now, I can clearly think about the theoretical way to get C. And it's tau or C1. You ask me, why am I thinking about that? Because C, it's a constant that is usually given, or it's something we have to calculate using this formula. This is the main two ideas that they ask about concerning the capacitance. Now you tell me we have R, okay, great, but we don't have tau 1. Exactly. This is why they gave you the graph for, so you can calculate tau. So how can I find tau before finding C1? Tau 1 is the time where the curve reaches 63% of its maximum value. And since the maximum value is 5 volts, we can clearly say that you see at the time tau 63% or 0.63 times 5. 0.63 times 5, that's equal to, let me use my calculator, 0.63 times 5, it's a 3.15 volts. And I go to the graph and I can clearly see 3.15. It's somewhere above 3 here. So the time tau 1 should be 0.02 milliseconds. Be careful for the unit. So tau 1 using the graph is 0.02 milliseconds. I have to convert this to seconds, so I have to multiply this value by times 10 to the power minus 3. Okay, which gives me 10 to the power minus 5 seconds. Okay, this is tau 1, and I have R, I can calculate C1, which is tau 1 over R, as I previously mentioned, the main formula. Okay, so tau 1 over R, so C1 is equal to 2 times 10 to the power minus 5 over R, which is 10 to the power 7. This would be minus 12 farad. Or we can say picofarad. As I always said, the value of the capacitance should be really small, not really big. So you have to be careful on how you're calculating. Now we calculated C1. Great. They only want 1. Now 2.2. Calculate M1, knowing that the relation between the mass of the object and the capacitance is C equals to. So now I calculated C. And I know that it's 2 picofarad. Now they want me to calculate M. I will write it here. C1 equals 1.066 times 10 to the power minus 12 over 1 minus M1. Okay. Preferably, you can cross multiply and find the value, the expression of M1 before replacing C by its value, preferably. So C1 times 1 minus M1 equals 1.066 times 10 to the power minus 12. Okay, now we take C to the other side, it is multiplied, so it will be divided on the other side, which is 1.066 times 10 to the power minus 12 over C1. And then we can take 1 to the other side, plus 1, it will be minus 1. So minus 1 minus M1 equals 1.066 times 10 to the power minus 12 over C1 minus 1. Then, to remove this negative sign here, we have to change the signs of the whole equation. So I will get M1 equals minus 1.00066 times 10 to the power minus 12 C1 plus 1 And now you can simply replace the values over C1, which is 2 times 10 to the power minus 12. Always we use the SI unit, always. Okay, which is M1 equals, we can remove 10 power minus 12 in the numerator and in the denominator. Now we have to find minus 1.066 divided by 2 plus 1. We will get 0.467 and kilogram is the SI unit. Okay, this is this part. Now, determine whether M1 is greater or less than M2. This question is really great because you can recalculate and do the same thing for M2. And once in the previous questions, they gave us the expression that relates C to M. Now you have the option to calculate C2 as I did with C1, then find M2, then state whether M2 is smaller or greater, but this is really a long type of problem. Okay, now I prefer to think deeply, more deeply, because C is equal to something over 1 minus M. That means C and M are inversely proportional. Let me tell you how. Since they gave us the expression, I can say C equals to that over 1 minus M. Okay, so C and 1 minus M are inversely proportional. What do I mean by that? If C1 is greater than C2, then M1 should be smaller than M2 and vice versa. So my keyword here is to calculate or to deduce from the graph which C is bigger so we can know about M. We can know more about M. Okay? Now, هون I mean 1 minus M1 is smaller than 1 minus M2. Okay, C and 1 minus M are inversely proportional. Okay, now here, look at the graph. You can clearly see that at 3.15, the value here that we got when we calculated the 63%, tau 1 is 0.02. However, tau 2 is almost 0.04 and a little bit greater too. It's somewhere here, 0.045, let me say. Okay, so I can clearly see from the graph that tau 1 is 0.02 milliseconds. However, tau 2 is 0.045 milliseconds. So since tau 2 is greater than tau 1, that tells me something about the capacitance, because tau is equal to RC. So if tau is getting bigger, then C is getting bigger, or R, but we're keeping R the same here. So what's really affected here is C, because we care about C now. C is changing. Okay, since tau 2 is greater than tau 1, then C2 is greater than C1. And now we just said that if C2 is greater than C1 and C is inversely proportional to 1 minus M, then 1 minus M2 should be smaller than 1 minus M1. Calculate that, continue on calculating that. Remove 1 on both sides. We will get minus M2 smaller than minus M1. We remove the negative signs, but by removing them, the sign of the inequality should switch. So M2 is greater than M1. As simple as that. You have this option and it's the smartest option and it's not a long pass. And you have the second option, which is the clear option. You can redo the calculation, redo the same. Calculate tau 2 and C2 just like I did here, but instead of 1, you put 2. Okay. And of course, you change the value of tau, because using the graph, tau should be bigger than 0.02. It should be somewhere here, 0.045, a little bit greater than 0.04. Okay. This is the first way to calculate tau. Once you calculate tau, you calculate C2 using the formula that relates them. Once you calculate C2, you have the expression that relates C to M. So you recalculate M2, and then you can state whether M2 is smaller or bigger than M1. Okay, but this is a really long method. It's fine. I know it's the easiest one. I know it's a clearer path, but you should write a little bit faster to not waste time. Okay. Thank you for watching. If you like the video, subscribe, share it to your friends. I'm trying my best to help everyone out there. So if you're watching, please let me know in the comments below if there's anything I can help with. Thank you guys.